Welcome back. The problem we're going to be looking at in this video is a combination of refraction through a fluid in addition to reflection from a flat mirror. And while this problem doesn't really fit in exactly in the type of context you've seen in your other problems, it's not as straightforward. It's very useful in that it'll allow us to practice our ray tracing skills and to also understand where virtual images arise from and what they mean. So keeping all that in mind, why don't you go ahead and read through the problem statement. As the problem states, we have a light bulb placed above a swimming pool some distance, d2, and the swimming pool is d1 deep. At the bottom of it, there's a large mirror. It's basically entirely reflective. The problem says if we stand right next to the light bulb and we look down at the water, we'll see an image of the light bulb somewhere below the surface of the pool. The question asks us, where is that image? And it tells us we can use a little bit about the small angle approximation to approach this problem. So because this problem is not quite as straightforward as some of the other lens problems and mirror problems, the best way to, I think, approach it at the beginning is to just draw some rays. So what we're going to do is take this light bulb, draw some rays, trace them out, and then we'll kind of get an idea of how that image is produced, and then hopefully we can use some Snell's law, trig, etc. to solve it from there. So I've kind of redrawn it over here. First thing we're going to do is draw a couple of rays coming through here and trace them out and see what they look like, how they traverse through the situation. The first ray, which is the easiest to draw, of course, is the one that comes down straight and hits the water perpendicularly. That won't refract at all because you have to be at an angle for it to refract. So it'll come down, hit the water, continue along its way, and then when it gets to the bottom of this, reflect back up straight. Very straightforward. So that ray will just look like this. Now let's look at another ray that's a little bit of an angle with respect to this. So if you have some ray coming out like this, the first thing that's going to happen is when it gets to this water surface, it's going to refract towards a normal because this is a lower index than this. So it's going to refract inward a little bit, come down here, and then let's draw that one first, and then we'll trace out what happens down there. So I'm going to exaggerate these angles. I know we're talking about small angles here, but I'm going to exaggerate them so we can draw the picture. Okay. Once it hits the water surface, it's going to refract inward. So look, something like this. Okay. Once it hits the reflective surface at the bottom, because it's a flat reflective surface, the angle of incidence always equals the angle of reflection. So it's going to leave at the same angle it came up at. Okay. That'll look like that. And then finally, when this ray of light leaves back out to air, it's going to come in at the same angle. It's going to leave the same angle it came in at because this is the same boundary with the same refractive index change. So it'll look like something like this. Okay, so what the light is doing is it's coming like this, down, back up, back out. This light just comes straight down and then reflects straight back up. Now, what we need to do is trace these rays back. So think about what's physically happening here. I'm sitting over here, and I'm looking down at the water. So I'm seeing all these rays of light come back up. The rays of light that have gone straight down and come back up, the ones at an angle that came back up. And I'm gathering all these rays. I'm only drawing two here, but I'm gathering a bunch of light rays that originated from the light bulb. So they're all the same color as the light bulb. They originated down. And what I'm thinking I'm seeing, though, is that I have no idea refraction took place. Your brain doesn't know that. What you think is that all the rays that come towards your eye are coming in a straight line. So you think that this ray of light, which hits your eye, actually originated down here. And this one originated down there. So you think that all these rays actually originated from some point below the surface. And that's what a virtual image is produced. So what we need to do is trace those rays back. And that'll help us use some geometry to figure out where these appear to have originated from. And that's the location of the image. This is the same thing we did in the thin lens video when we had to draw the when we had to draw the virtual image from the convergent lens. We traced them back to see where their common origin was. Okay. So, and if you draw a bunch of other rays, you're going to basically get the exact same point. They're all going to originate from there. So they all kind of look like that. So this is the location of a virtual image, and this is how, this is the location, this is the distance we need to find. Right, so this is x, which we're looking for. We have d1 here, d2 here, and let me go ahead and label a few angles while we're at it, so we can start using Snell's law. So let me just draw the normal here. So I'll call that theta 1. Theta 2. Likewise over here, these are the exact same angles as that one. Okay. We can actually label one more angle in this, so we can figure out these guys just using the fact that this is an isosceles triangle, but let me figure out the angle down here. So that angle is originating from this line. The angle between this line and the vertical is theta 1. This angle is also theta 1, not theta 2. Keep that in mind. It originated from this line, not from this one. So this is theta 1 as well. Okay. And now we just had proceed by applying Snell's law, which will give us a relationship between theta 1 and theta 2, and by using some trigonometry and geometry. Let me first write down the Snell's law. So Snell's law says that n1 times sine theta 1 is n2 times sine theta 2. n1 is just 1 because it's air, n2 is the refractive index of water. So we have sine theta 1, again n1 is 1, and n2 is the refractive index of water. We can also use a small angle approximation here. And the reason we can use that is because we're very close to the light bulb here. So all these angles, I've drawn them huge, but they're actually going to be very small. We're only going to be talking about the rays that are like very close to the normal. They're all going to be a very small angle, so we can use this approximation, which says that you can replace all the sines with just the thetas. Now let's proceed by applying a little bit of trigonometry. So I'm going to look at this big triangle right here, because it has the x we're looking for. So this triangle has the quantity we want. So let's just use this, some trig right here. It's got theta 1s, which are related to over here, so hopefully you can relate them to by using Snell's law. Now, we need to use trig, so we either need to know the length of this side or the length of this side. This side is probably going to come up in some other tricks, so let me just label this with some quantities, which we don't know, but hopefully we can solve for with other equations. Let me call this distance A, and I'll call this distance, note that this is an isosceles triangle, so I'm just going to cut it in half and call this B on each side. So the first relationship I can use is trigonometry on this triangle, which gives me the tan of theta 1 is the opposite over the adjacent. Opposite is all this, 2b plus a. And the adjacent, as you look at the picture, is d1 plus x. All right, so that tells me, again, if I use a small angle approximation, I can replace theta, I can replace tan theta, which is theta. And let me go ahead and solve this for x, because that's what we're looking for here. So you get x is 2b plus a over theta 1 minus d1. All right, so it looks like we need to know either what theta 1 is, which we certainly don't know because we're looking at a bunch of different rays, or we need to find a way to put b and a in here in terms of thetas and hope that the thetas cancel out. That's what we're going to do. So I want you guys to find a relationship for b and a in terms of the angles here by using a little bit of trigonometry. And then once we plug those in, we should be able to get this thing in closed form. So go ahead and try that out, and we'll finish up the problem. To find A1, we're going to use this triangle right here. Notice that this angle is theta 1, which means this angle is theta 1. Okay, so applying trigonometry on this triangle, you're going to have the tangent of theta 1 is a over d2. And then again, we can use a small angle approximation to just make this theta 1. So if I solve for a, I get a is theta 1 times d2. For b, I can use this triangle over here. Now this right here is an isosceles triangle. The whole thing is isosceles. This is a right triangle if I just cut this guy all the way down like this in half. And it looks like, actually let me just use this one instead. So this one right here is a right triangle. And you see that this distance, of course, is b. So tangent of theta 2 is opposite b divided by adjacent, which is d1. So you get tangent of theta 2 is, again, opposite over adjacent, b over d1. So this is approximately equal to theta 2, so I get that b equals theta 2 times d1. If I plug those in here, we get that x equals, oh, you know what? Let me do one more thing here. Let's go ahead and write this in terms of theta 1 by using Snell's law, because then we can cancel out all the theta 1s, hopefully. So theta 2 is theta 1 over n2. So this equals theta 1 d1 over n2. I'll plug that in for b. So then I get for x, I get 2 times this quantity, so 2 theta 1 d1 over n2. And then for a, we have this guy, all over theta 1. So, and then minus d1. So as you expected, the theta 1s will cancel from every term in this fraction here. So you just get 2d1 over n2 plus d2 minus d1. We know all those quantities. This is 1.33 for water. And we know d1 and d2, so that just gives us, when you plug in the numbers, 351 centimeters. Okay. Now, this is basically, it looks like you would appear, when you're looking up here, the light bulb would appear that it's 351 centimeters below the surface. We can actually check this by removing all the water and pretending it's air. In other words, imagine that we're just looking down at this mirror. There's no water here, but we're standing this distance above the mirror. In real life, where would we actually be? If we just had a mirror at the bottom of a pool, it would look like our image is exactly how far above we are. This is what happens when we look in mirrors on our wall. So if we didn't have any water, we should expect that the image would be d1 plus d2 below the surface. Is that the case? If we had no water, then this is just equal to 1, right? Because water has a refractive index of n2, but air just has a refractive index of 1. So if we had no water, we'd have 2d1 plus d2 minus d1, which would give us d1 plus d2. Does that actually make sense? Write that over here. So check if n2 equals 1, in other words, water goes to air, then we get that x is just how far we are from the mirror, which is what we'd expect if we look at a mirror. We would see ourselves the same distance we are away from the surface of the mirror. So that's the answer to this problem. As you see, we had to draw a couple of rays, and we were able to trace them back to the originating point, and that tells us where the virtual image is. And from that point on, we just had to use Snell's law and a lot of trig. If you have any further questions, or you want to go back and look at the math in a little more detail, look at the attached solution, and we'll see you next time.